First below sea level. The purpose of this group is really just to get people in town who are interested in systems programming together. But I don't really consider myself a hardcore systems programmer. I have a lot of experience in the application domain and a bunch of other places. And there aren't really a lot of us in the city, I think. So, to me, it's also kind of just a place that's will hopefully be a place that's, not intimidating and people can kind of learn some interesting things from systems programming, even if they're not doing that for their day job. And it's, Aaron and myself, Aaron's over here, are organizing this thing. I've been doing software engineering for a pretty long time, maybe 15 years or so. And Aaron's been doing it for equally as long, right? But yeah, we're always looking for more organizers or anyone to help or do a talk. That brings us into general administrative business. So we're going to do this the first Tuesday of every month. I'm doing this talk today based on it's just kind of a continuation of a talk I did last week for Dustin's group. Aaron's going to do a talk on next time about load balancers and this maglev paper from Google. There's like a Google paper, right? Yeah. We're looking for someone to fill in the April spot. I guess it would be like April 2nd. May 2nd. So if anyone has an idea for a talk, come let us know. If not, then I will talk about something about WebAssembly probably. And that brings us into, do you have something to say?
I was going to say there's a list of potential ideas on the About section of the Below Sea Level page. Any kind of projects you're working on? I'd love to have a home lab meetup, or if anybody is really into home lab and wants to kind of show setting up their own, how you actually architect like that. I think there's all kinds of stuff we're really interested in. So after the talk, either of us will super happy to talk about it. So. Yeah,
we'll pitch you the ideas ourselves because we have tons of ideas, not enough time to do it, and we could pitch you ideas that work for you. To me, it would be really cool to get someone to be like, I've never done this before, and I'm going to try and do it. I think that'd be a really, really cool talk. And that brings us to our sponsor, the pizza in the room, sponsored by Dilipso. This is my company. This is a company we started to take WebAssembly to production. And we're working on accelerating the adoption of WebAssembly, building a lot of tools around WebAssembly. And if that's something that interests you, either from a perspective of someone who's like, what is WebAssembly? Or maybe I'm interested in it. Or if you're interested in, maybe working on WebAssembly, come talk to me. I'll talk your ear off about this stuff for days. But thanks, Dilipso. Anything else before we start, Aaron?
You got it. Okay,
great. So let's get started. So this is a talk I gave about a week ago, and I gave it for Dustin's group, which is, it's meant to be more of kind of a general audience of software developers. So I wanted to do something that was kind of let's dig into something kind of like my stuff in my day job, but a little bit more approachable. And I've always had this idea, it'd be really fun to write a virtual machine in a very accessible language, JavaScript, live in front of everybody. And it was a really terrible idea. And I didn't want to do it because it's just I'm going to code JavaScript live in front of everyone. It's a terrible idea. But I was like, no, I'm going to finally do this. It'll be fun. I need to step up and do it. And I created this thing called Smol, and this is on GitHub. It's just a little project where basically it's a virtual machine in JavaScript, and I broke up all the folders into these versions, and each version, version 0 starts off very simple. And it can do basically an adding machine, and each version gets a little bit more complicated, but they're all like kind of bite-sized steps. So in theory, if you can kind of understand what we're about to build, we're going to build kind of version like 0 and 1. If you can follow that, then you can follow this to the end. And ideally, I want to push this really far and like have a self-hosted compiler for its own language and a bunch of goofy stuff like that. But I only had like a month, and I just stopped at V3. I might pick it up and keep going. So let's get the presentation started. So again, who am I? Well, the relevant part is I'm the co-founder of Dilipso. And like I said before, that our focus is on WebAssembly. And if you're not too familiar with WebAssembly, you can sort of think of it like a language agnostic virtual machine. And it's a stack-based virtual machine. And it's very similar to what we're about to build in architecture. I mean, obviously it's much more complicated in the performance and like all the other ways that a real piece of software will be. But architecturally, it's the same kind of idea. It's just a stack-based virtual machine. So I spent a lot of time in the last talk talking about kind of what is a virtual machine. I'm going to kind of breeze through a little bit some of this stuff because I feel like we probably get it. But if you're not sure of something, just let me know and I'll do a tangent. So when we say a virtual machine, a lot of people often think of this thing on the left. And those are the things that we run in our clouds and our data centers and on our laptops. And we generally call these system virtual machines. And what they are is they emulate an entire computer. So the entire stack of hardware, they have the display, the graphics, all that stuff. The input of a system virtual machine is generally an operating system. So an operating system runs on one of these. We're not really talking about that. What we're talking about is what we commonly call a process virtual machine. And a good example of this would be the Java virtual machine. And these are more akin to emulating like a Unix process. They're these things that power all of our favorite programming languages. If you use Java or JavaScript or Python or Ruby or Erlang or .NET, all those things, their compute is done on a virtual machine. Let's just do some like definition stuff. What is a machine? I look at a machine as just like it's got a well-known set of rules and a configuration, and the configuration is the program. And there are two categories. There are like abstract machines, and these are things that maybe can't exist, or they're built, they're designed as a thought experiment, or in this virtual way. And there's physical machines. These are the things that are actually like hardware, like CPUs, the real physical things that we run code on. What is virtual? I look at it sort of like it's another fuzzy kind of definition. I sort of look at it like from the perspective of the program. It like thinks it's living on a real machine, but it's really like a construct that you've created. And I want to take a quick moment to say I would not look at programs as like sentient or understanding like where they are necessarily. Hopefully by the end of this talk, you'll understand that programs are really just like a configuration. It's more like a path that the machine runs down than it is like its actual own organism. If anything, the machine is the thing that's actually alive and is sort of thinking, if you want to have that philosophy. All right, let's talk about native code. So we all know that C doesn't have a virtual machine, right? And when you write a C program, it compiles directly to run on the machine and the operating system. So here's a really simple program that adds two numbers, returns a result. And if you compile this, your operating system will tell you it's a Mako ARM64 file. So Mako, because it's an Apple, I'm on an Apple here. ARM64, because my chip is an M1 chip of the ARM architecture. And we call this native code. It's meant to run directly on the CPU. The CPU understands how to read this. So if we look at the actual file, we just see it's a bunch of bytes. And those bytes, some of those bytes have human understanding. They have metadata, some text. Most of them are really only understood by the machine, or it's just padding of zeros. But somewhere down there are the actual instructions that the computer sees that let it know to add two numbers. That's the actual code. And really quick, if I say like just a bunch of bytes or hexadecimal, is everyone like okay with that? Okay, I'm actually going to also take a moment to take a break. If anyone has any questions, I'll occasionally jump to the Slack. If you have any questions, just start typing. There is a lag, so like if I don't see you, I'm going to miss it. But I'll try and like kind of come back into the Slack and see if anyone's asking any questions every once in a while. And if I don't get you, I'll stop soon. And all right, let's keep going. So yeah, these bytes, the machine knows how to read, turn it into an actual running program. Now let's look at a Java file. So this is a Java file that does the same thing. When you compile it and you ask your operating system what it is, it's going to say that's a compiled Java class. And when you look at that, it looks fairly similar. It's just a bunch of bytes. Some of it is metadata. There's like actual ASCII text in there. Down there is where the add instruction is, and that's the thing that tells the Java virtual machine to add these two numbers together. A funny little anecdote, I didn't realize this, but when I first opened this, I realized I thought it was an accident that the first 4 bytes were Cafe Babe, but apparently that's like that's how every Java class starts. And I wonder if they regret that or not. Yeah, so again, just to kind of recap, our virtual machine emits something that we call bytecode, right? It's not native code. It's code that targets the virtual machine. And generally, if you look at what the virtual machine itself is written at, it's usually written in native code. So here, the Java virtual machine itself, the thing that runs the Java program, is written in native code because it needs to be fast. But it doesn't necessarily need to be written in native code. For instance, we're going to write a virtual machine in Node in JavaScript, which itself has a virtual machine. And in theory, you could just keep going all the way down. I think at some point you probably have to stop and hit it native code, but you get my point. Like the program doesn't really care. Does that make sense to everyone so far? Okay, before we jump into bytecode, I'll take a quick second to see if anyone... if anyone is like having any problems with this, I am recording this. I'll post it to YouTube or something later. Sorry, I'm learning about Twitch, so it's not a great stream. I apologize. But next time I'll have it figured out. I'm gonna buy some hardware. I'm gonna do it right. I'm gonna turn into a PewDiePie by the time I come back.
So why did you decide to write this in Node?
Oh man, good question. I totally skipped all that stuff. Like, why am I doing this? Yeah, so I wanted it to be, my goal of this is like to demystify the virtual machine. Because if you look at, like if you ask someone like, I want to learn how a virtual machine works, they'll be like, oh yeah, like V8 is open source or something. And, like there's a lot of stuff out there, and even a lot of the educational stuff, it's like all written in C, or it's got, just so many layers of performance and a bunch of other really like useful things. But just to understand the concept, it's kind of like, it's inaccessible. Like if I were like a front end developer, and someone was like, oh yeah, just read this article about this guy writing this thing in C, I'd be like, I'm not going to learn C to learn this concept. So for me, it's really just about reaching as many people as possible, making it just very straightforward, and just teaching the concept of like, this thing's very simple at its heart. It's not kind of a magical thing. Does that make sense? Yeah, great question. Thanks. I completely forgot to talk about the motivations. All right, so now let's take a quick tour of bytecode. We're going to look at bytecode for the machine that we're building here in this talk. And yeah, how do all these symbols turn into like a living, breathing program? How does the computer interpret these things? So I like to think of bytecode in all like computer memory. I think the simplest way to think of it is just an array. And it's kind of just like an array of numbers. Like that's really the simplest way to think about it. And when you index into that array, that's generally called an address. And yeah, it's just a bunch of bytes, and the computer just walks through and interprets them. So we're going to describe that process. All right, let's talk about first like what these bytes mean. So with bytecode, you can generally break it down into instructions. And instructions are, I think about it kind of like the API of the machine. As the person who's designing the machine, you decide what these are, what they're named, and what they do when the machine sees them. And instructions can have like operands, or they could not, but they all start with an opcode. And an opcode is just a magic number is a constant that says like what this instruction is. So we have 3 instructions here: push, add, and halt. And what this program does is it pushes 2 numbers. It pushes 20 and 22 onto the stack. It adds those 2 numbers, and then it halts the program, which means it kills the program. I'll explain what all that means in a minute, but that's what this does. Does that kind of make sense to everyone? Okay, great. So let's actually talk about what are the steps to run this program. Every machine, whether it's physical or an abstract machine, follows 3 steps: fetch, decode, and execute. And it just follows these in a loop. And so what fetch does is it will grab where it's at in memory. It will grab that instruction. Decode will decide what it is and what to do with it. And then execute will change the state of the machine. And it just does that loop over and over again. And when I say state of the machine, our very simple machine, we only have 2 pieces of state. You have something called an IP, instruction pointer. And you can think of that as just a index into the array of where we are in the code. So as we move the instruction pointer up or down, we can go forward or backwards in the code. And we have a stack. And a stack is just you can think of it like it's just a temporary place where you can put some numbers for operations to deal with later, and to work on. So the instructions, like the add instruction, expects things to be on the stack. So you can also think of it as kind of like, it's sort of like parameters for a function call. Like you're putting things into the stack, and then when an operation sees them, it can operate on them. So let's go through this program. This is the same program as before. First thing we do is we fetch, and we see this is the push instruction. And we're going to get the number that it wants us to push, and we're going to put that onto the stack. And down here I have a little pseudo JavaScript code that says what it's doing. We're just pushing this number onto the stack. And does everyone know what a stack is? Like, it's a data structure where you can push things on the end and then pop things off the end. And JavaScript has push and pop on the array. So you can think of just a stack as just an array that you can only put things on the end of it and take things off the end of it. So we do it again. We see push again. We push this number onto the stack. We see add. So the way that we programmed add, it expects there to be 2 numbers on the stack. So it pulls them off, it adds them, and then it puts the results onto the stack. And then we call halt. Generally, we would do something with the number. We'll do that when we build the thing. But does this make sense so far? So that's all it really is. It just goes in a straight line, incrementing the instruction pointer to the next instruction. It just keeps going, keeps going, keeps going. It just does those 3 things. Let's see if the chat has anything to say. And then I'm going to actually start coding. which again, last time I did this, like I only made like one mistake, and it was a miracle. So I don't, I don't think I'm gonna get away with it again. So if y'all notice me making a mistake, please tell me. Okay, no one's speaking up. So
I have a question about
Yeah.
the stack. So that, I mean, that has to be stored somewhere, but I presumably it could be stored in like different places, like maybe on the
Oh.
CPU cache, or it could be in RAM, or on the hard disk, or.
yeah, so in our virtual machine, so it depends, right? In our virtual machine, like we don't have to worry about where it really lives, right? So we're just saying, let's just use a JavaScript array, even though that doesn't make any sense. It's just the simplest way to explain the idea. In reality, stacks are put in a number of places. Generally, it's somewhere in the memory, and yeah, it ends up being cached on the CPU. But generally, it's in the memory with everything else. And as you go through the versions in this program, in this small virtual machine, at some point I implement this, which is like putting all the memory together, and the stack goes in there too. So yeah, I mean, the question of where it lives really depends on like, is it a real machine? Is it a virtual machine? And what did the virtual machine programmer, where do you want to put it? Does that make sense? So
Yeah.
for our case, it's just in a JavaScript array. But yeah, it can be optimized into a number of different places. Okay, no questions from chat. Let's write some code. Oh man, it made it really squishy. Can everyone see this, or should I make it a little bigger? This is good? In the back? Okay. Yeah. So let me make this full screen too. That might help a little bit. All right. So let's start off by writing our program. Oh, actually, so let's start off with the first step. We're going to look at our instruction set. I wrote it down over here. And I'm just going to write some of these constants down and give them names so that we don't get too lost with magic numbers everywhere. I added one instruction here called emit, and emit is just going to take the number off the top of the stack and print it. That way we can actually see what our program is doing, because that last program didn't do anything. Okay, makes sense so far. We have some constants. So now we're going to write the program in the bytecode form, and we're just going to put it in an array. So we're going to push 20, push 22. We add, and then we emit, and then we halt. And I'm going to log this out and just make sure that everything is working. So I'm just using Node to run this, and it's just a simple JavaScript file. Makes sense so far? So that's our program, right? That's what we saw before, except now we have emit, but it's the same program, it's just an array of numbers. Okay, so now let's write our code. Yeah, so in order to write the machine, first thing we need to do is we need our state. So remember before I said we have two pieces of state. We have the instruction pointer in the stack. And to actually make the machine run, the simplest way to do that is we're just gonna do an infinite while loop. And we will break out of this while loop when we run into halt. So inside this while loop, we'll do our fetch, decode, execute cycle that we talked about before. So we got to do those three things. So first thing is we got to fetch the opcode. We got to say, what is our opcode? And I'm making judicious use of the plus plus here. Just know that it's a little older semantic thing from C where it just, after this statement is done, it'll increment instruction pointer, because we need to, basically what we want to do is part of decoding, we will, like when we know this is a push, we know that it has one operand. So it's up to the decode, it's up to the push's like little code block to consume those operands until the instruction pointer is at the next instruction. And so that way, every time we get back to the top of this loop, we're going to be at an opcode and not in the middle of some code somewhere. So now we can switch on this opcode. And we're just going to do it one at a time from our code here. We're just going to run through it as if we were reading the code ourselves. So first thing we're going to do is we're going to see push. And to implement push, we're just going to push that value onto the stack. And I'm going to do this plus plus again because we want to end up back at the next instruction. And yeah, so basically I'm asking for the, right here IP is 0, right here IP is 1, so I'm getting the operand for push. Does that make sense? So I'm pushing 20 onto the stack. Should work. So we do that once, we got 20 on the stack. We do that again, we got 22 on the stack. Now we're going to get to add. And for add, we're just going to pop the two values off the stack. And we're going to push the addition of those two values onto the stack. And then we need to break, or else all hell breaks loose. And this is why it's like a tightrope doing live JavaScript coding. Because that's the kind of thing you don't see until you're just so embarrassed. Okay, making sense so far. Now we're gonna run into emit. So for emit, I'm just doing console.log, and I'm making emit a destructive act. It's going to actually pop the value off top of the stack. So emit will consume whatever is there. The last thing we do is halt. And for halt, we're just going to return from this entire function. So we're just going to get out of the function. And I've learned the hard way that I need to put a default case and throw an error, or else, if we end up like in the middle of some operand or something, like there needs to be some kind of Oh man, thank you so much. All right, I love this group. Okay, so yeah, that'll just make sure that if we do make some kind of mistake in the course of this, it won't be too confusing. Yeah, so let's look at this. I think it's all right. I'm going to give it a shot. Oh, thank God. All right, so it worked. I printed out 42. That's the addition of 20 and 22, and that's a virtual machine. So that's basically it. I mean, like that's kind of all it does. It just does that forever. But yeah, so it really is painful to, like, I want to write a bunch of software. I want to write a self-hosted compiler in this. I'm gonna have to write software in this kind of raw native form. Like I can't have a programming language without some code to interpret it or compile it or something. So am I going to write all this code like this? No. That's generally where we turn to assemblers. So we're going to write an assembler. And yeah, I mean, like, if this was a JVM, the JVM takes a binary file, you pass it in as an argument, and it runs that binary file. So we want to do the same thing. We want an assembler which can take some high-level assembly language, assemble it down into binary form, and then we can run that. And in theory, we could write like a whole compiler outside of this, but I would like to keep it all in the machine. But you could. So to do that, we're just going to do the same thing we were doing before. except instead of writing it in here, we're just going to use node's read file sync method to get a binary file from our command line and just turn that into an array buffer. And the code should be the same because an array buffer it has the same interface as an array. So it's basically just an array of numbers. You can think about it. So let's talk about how we do this. I'm not going to write it by scratch because that would just take too long and not be super interesting. So I'm going to use this thing I've used before called custom-asm. And if you've ever written a programming language or done anything like that, you might have used something called a parser generator, or you've used some other kind of code generation tool. And custom-asm is like an assembler generator. You can describe in a high-level way what your instruction set is, and it will map the assembly language to that for you. So it just builds the assembler for you. And it's a really neat tool. I've used a bunch of times for experimental stuff. It's really good if you're like building your own CPU or you're doing something like you're trying to write a Super Nintendo game or something for an emulator where you maybe don't have a tool set to build programs in a nice high-level language. You just know the bytecode. You know the instruction set. So how do we use this? I have this file called smol.asm. And all you do is you just basically tell it, like everything on the left of these rockets is, the kind of template syntax for what the assembly language is, and then the things on the right are the kind of small instruction set stuff, right? So push, we remember has a opcode of 1, and then add has an opcode of 2. Emit 4, halt 5. Make sense? So now let's go in and actually just write some assembly. So we'll just write the same program we had before. And to compile it, you just run this program like this. I'll do a little print to show you what this does. It basically just creates an array of bytes just like we had before. Dumps them to disk in this binary file, and it has this nice little formatter that tells you, what the bytes map to. But if you actually just look at the binary file that we created, it's just it's the same array of bytes. These are hexadecimal, so it's 14 and 16 instead of 20 and 22. But you get the point. These are the same. It's the same thing. And if we run it and we pass it our binary file, you see we get the same answer and we see the same code, but it's in a buffer now. That makes sense? Cool, so now we have an assembly language. So this is neat, but it's not Turing complete. There's only so much you can do with this. You can get pretty far with just adding numbers. You can get a lot farther than you think with just adding numbers, but the big problem that we have is that programs don't go in a straight line, right? Like programs loop, you jump to functions. You need ways to jump around. You need ways to manipulate the instruction pointer. And specifically, you need a way to conditionally manipulate the instruction pointer so that you can actually have the full power of a Turing complete language. Because if you could imagine, I want to build a programming language on this, right? How would I implement loops? How would I implement if statements? There's just no way to do that with this instruction set. So we're going to do that. Before we do that, I'll check the Slack. No questions. So I have two other instructions. One is called JNZ, jump not zero. One is called JMP, jump. And let's write those down. And JNZ is 8. Jump is 9. Is that right? Yeah. And these both have an address as an operand. And I'll explain what they do. So for jump, it's probably easier just to code it up. For jump, what we're going to do is we're just going to set the instruction pointer to where we're at in the code, right? So code at IP here is going to be the operand of jump. So if we say jump to 0, it's going to set the instruction pointer to 0. The program will start over. And I got to go implement that real quick in Smol. I need to tell it. I'm just going to tell it. And it was it 8 or 9? And this is address, and then 0. So I'm just telling Smol. I'm telling custom-asm. Jump is a instruction that takes one operand and it maps to this instruction code, opcode 9 with an 8-bit value on the end. So let's make it jump. Let me go back to our program here. So one simple thing we could do is just say jump to 0 right here. So what this should do is it should just print 42 over and over again, if I didn't break it terribly. Oh, it worked, cool. So that's sort of cool. I think it's cool. But yeah, you could imagine okay, this sort of invokes the old days of basic, what it's go to line, whatever, and then it's someone comes and they write some code up here, and then it's this no longer is valid. That's why custom-asm has some nice things. One of them is which is a label, and with the label construct, you can say this. You can label a sort of line in the instruction, and it will associate that with that address in the code. So you can later reference that point in the code with an actual name, and that will put the 0 there for you. And if you change it, it'll move it around. And something I've been doing as a matter of habit is doing this little bootloader thing where I basically, if you're familiar with C or even in Java, there's typically an entry point into your program. And here we're just going to call that start. That's a convention. And this is just going to tell us if this is the first instruction, it just says jump to start, then we can just put code anywhere in here. And when we run the program, it's just going to jump to the start. So that's kind of our main. Does that make sense? Yeah, so let's do jump not 0 now. This is the thing that's actually going to give us the real power. Jump not 0 is, so the semantics of jump not 0 is it will jump, but only if the top of the stack is not 0. So first thing we need to do is get that value. I'm going to call it a predicate. It's think of it like a Boolean value. So we're going to pop it off the stack. We're going to get the address here that we want to jump to. And I'm incrementing it here because there are two things that could happen at this point. It could jump or it could not jump. So if it doesn't jump, we need to make sure we're pointing to the next instruction. So then we'll actually do our if statement here. We're going to say if it's not 0, then we're going to jump. And for jump, we're just going to say IP equals the 2 address. And then I think we need to break. So does this make sense? So all we really did was just add a conditional, and we're only jumping when that happens. And it doesn't seem like much, but it gives you a lot of power. So let me explain. Let's create the semantics of an if statement here. Let's go back to our program. let's say like I'm writing a language and I want to have if else, and I want, if the condition is true, I want it to run that block, and then skip the else block and then run the next block. If it's false, I want it to do the other thing. I want it to go that other path. So we're going to kind of emulate like a whole if statement here. So I'm going to create two conditions. One we'll call print 42. Also, custom has them as this thing called inner labels. So if you start with a dot, it's just a label inside of a label. And it's really more of a convention. It doesn't really mean anything. This is just another label. So we'll have two places that we can jump to. We'll have print 42, which will print 42, and then we have print 99, which will print 99. And what we want to do is we also want to, let's push 0 and make it false. So what we want to do is we want to say, okay, let's do a conditional where if the conditional is true, we'll jump to this, and then we'll jump to here. If it's false, we'll jump to this, and then we'll jump to here. Does that make sense so far? So we're just doing an if-then statement. So we'll just hard code a value that is not 0, and we'll use our jump not 0, and we'll say if the value is not 0, then jump to 42. Makes sense so far? So if it's not 0, which it's not going to be this time, jump to 42, print that. The problem is, then we just fall through, right? We just fall through and we push this. So what we need to do is we just need some kind of other label here, and then we'll just jump to that. And we'll go ahead and do the same thing here, even though I don't think we need to. So this allows us to jump to these and then jump to the next piece of code that's after it, after this if statement. So, how do we do the other condition? Well, remember, if it's not 0 here, we'll jump to 42. But if it is 0, it's just going to run right through that line. So then we know that if we get here, then it was 0. So we can just jump straight to 99. This makes sense? So now we have like all the semantics of an if then else kind of situation. So let's try and run this, and hopefully it doesn't explode. Yeah, so it's 42 this time. And then if we had 0 on the stack, it should be 99 and 0. So now you can kind of see, like, okay, if I were creating a programming language, I could maybe write some kind of compiler that emits this when it sees an if statement. It just kind of creates these inner labels and tells it, it maybe wouldn't have labels, but you get my point. Like it would be able to, with the jump not 0, it's able to do enough to kind of emulate any condition, right? And like, let's say you had a big switch statement, right? Like you could just be doing jump not zeros all the way down until you get to a default, right? So you can think about how you might do all these different conditions in your programming language. Does that make sense, everybody? Okay, cool. Let's keep going. So one thing that you need is, this is cool, but it's like how do you jump to something and then back, right? Like, so how do you do a function call? How do you jump to a piece of code and then jump back? Because if I had a piece of code over here and I said, that's my code, how I can jump to my code, but how do I jump back, right? It's like I gotta create a label. Like it gets really messy really quick, and it's hard to figure out exactly what to do. So what we're gonna do is we're gonna add a call instruction, and this is gonna give us like kind of something like a function call. So we'll have a call and a return, and this will allow us to jump to. It'll basically allow us to do a subroutine. It'll allow us to jump to a label or a block of code, and then return back to where we are. Does that follow so far? I forgot what let me go see what the instructions I forgot what the opcodes are for this. Yeah, here they are. I'm just going to copy these over to here. Oh, I gotta actually take all these. I gotta take all these off. This is later. This is later on, and we don't have 32-bit values. We have 8-bit values right now. So yeah, we have call, and that has it looks similar to jump. It's opcode 6. We have return, and all it does is return us back. So there are a lot of different ways to do this. Typically, the way people do this. Well, let's just start coding it up, and then I'll explain. All right, let me get back. So it's call is 6, return is 7. All right. So I'll explain the problem as I coding this up. So for call, we want to know some kind of address, an annoying scoping problem with JavaScript switch. For call, we want to know the address. I don't really need to do this, but it doesn't really matter. And we want to jump to that. So it should look similar to our jump, right? The problem is, yeah, how do we know how to go back? So there are a variety of ways to do this. Typically, what you'll see machines do is, and what you'll hear often, is something called a stack frame. And this is a way to like make a call to a function or subroutine, and it kind of creates a watermark on the stack. And it allows you to put all sorts of stuff on this. Well, one thing it does is it puts a few certain things on the stack that it needs to get back. So it'll put a return address to where you came from. And it'll also allow you to put a bunch of stuff on the stack. And then when you call return, it basically just wipes all that stuff away. It just forgets it. It's like, okay, you can just put whatever you want there, and we'll just wipe that whole frame away, and we'll find the return address and then come back. The way I'm doing it is something I borrowed from the Forth programming language. It's a simpler way to do it. Is I have a second stack called return stack. And I'm just going to use this stack just for return addresses for functions. So anytime we jump to a subroutine, we're going to put the return, we're going to put the, our instruction pointer on the return stack. So here, before we jump, we're going to say return stack.push IP. And that's going to allow us to return back to this place later. There are pros and cons to doing this. It's much simpler to do, but then it kind of creates some burdens. As a programmer, like if you write a subroutine, you have to make sure that you clean up your stack, right? But like you really have to care about what comes in and what goes out. But that also kind of gives you a cool opportunity to do like interesting things where you can push like multiple values on the stack, and then you can return multiple values on the stack. So it's like you have like variable arguments in and out of these functions, right? So they're like functions without any calling conventions. You can just say, I left a bunch of stuff on this stack, I call this thing, and then when you're done, like you've left the stack however you wanted, right? And if you look at a language like Forth, this is kind of its operating model, and it allows for some very interesting things. It puts a little bit more burden on the programmer and the software, but that's fine. It makes for a simpler machine. So now we do our return. And for return, all we should need to do is we just need to say our return stack, we just need to pop it off and then put it in the IP. Right? So we're just getting that return address back and then pointing the IP back at it. Does that make sense to everyone? So when we jump, we're saving where we are, and when the function is done and it calls return, it brings us back to where we were. And you could see how this could also allow you to do nested subroutines, right? Like you could just kind of keep going until you run out of stack memory, which, you know, on an actual machine is going to be, you're going to run out quick, but on our machine it's, you know, infinite basically, as big as a JavaScript array can be. So we don't need to worry about it. Okay, let's see if this works. I don't know if this is going to work or not. So let's create a print 42 here. We're going to push 42. Actually, no. To demonstrate like the stack stuff, let's just say print top of stack, right? And then we'll return. And we're just going to push some value onto the top of the stack. We're going to call print TOS. That's our label there. And then we will halt. So this gives us a way to like basically pass arguments to this subroutine. So we're going to pass 42 to it. And let's see if this works. It works, cool. And you know, it could also return things too, right? Like it could return something here. It could return 99. And that didn't work because yeah, I'm not sure why that didn't work. That's where things get tricky. We'll just cheat. Let me just make sure I implemented this correctly. Oh wait, this is a much later version that we need to look at. Oh, you know what it is? Of course, off by one error, right? We don't want to return to where we were. We want to return to the next, right? Because like we were, right now we're on instruction, say 4. We don't want to return to 4. We want to return to 5. We want to return to here. So we should say when we do a return address, we should return to the next address. I think that should work. Yeah, there we go. Does that make sense? So yeah, I was naively just like putting where we were, but we want to come back. When we come back, we don't want to be on call. We want to be on emit. Cool. Yeah, so that's probably about as much coding as I want to do, because if I keep going, then things get really hairy, because I have to, it gets hairy once we go to like 32 bits, and then, yeah, it's just a little bit too much coding for this, and I think that we can kind of just, you guys are probably getting the point enough. So we'll just go look at the other versions. So what I coded was basically up to V0 or V1. When we get to V2, what we're going to do is we're going to, and what time is it? 7:23. When we get to V2, we're going to unify all the memory. So that's another thing, we didn't really talk about memory. In V1, I have some instructions to load and store bytes in memory. And memory is like just another array. So we're just adding a bunch of state to our machine here. And I'm judiciously using JavaScript arrays because it's just so simple to reason about. But once we get to V2, we get into a little bit more of the advanced stuff, and everything in V2 is just in this, it's just in memory. It's just one array buffer, a 32-bit array buffer. And instead of, this was that diagram I showed earlier, instead of having separate arrays, we basically just have one big block of memory, and we just have pointers into these things. So we just kind of reserve places. Like, okay, everything on the top of this array is for the stack. Everything on the bottom is where the code lives. Everything above that is where all like the static variables live. We have our heap memory just above that, and that can kind of grow or shrink. And our stack grows down and our heap grows up. So it's a little bit more like a real virtual machine. So we get to that, and we put an actual stack limit. In V3, so in V2, I also have like a little bit more I/O stuff. I'll show you what you can do with that. So first off, you have like kind of just enough to, in V1 you have just enough to do like Fibonacci. In V2, you can do things like strings, like you can store strings in the static data, and you can print strings, and you can do some basic I/O. So here's like a little guessing game I made. It doesn't have any access to random numbers, so the answer is always 7, but it works. So it's a game that you could play one time. And then we go to V3, and this is where I was like trying to do kind of syscalls. So I made a syscall operation, and this allows me to like interact with the operating system a little bit. I can read and write files. I can read and write from standard in and standard out and do all that kind of stuff. So from here, I could probably build a lot more features and some more interesting things. But this is kind of when I was like, I ran out of time because I was just doing this kind of, over the course of a few weeks and on my free time. But I could keep pushing it here. And yeah, that's it. That's as far as I got. But you could see maybe at V4 is when we start looking at like, okay, let's write kind of more of like a little standard library of some sort. And then from that, we could write a simple fourth, like some kind of language that can bootstrap itself. And then you actually have you can write your own programs in the language. We could actually get to a point where this is more of like it's like a real kind of interesting, fun machine. And yeah, I think that's it. I think now we'll just get to questions and chatting about some of this stuff because I'm out of slides. Yeah, that was my last slide. Cool. Any questions? And feel free to chime in on the Slack too. Anybody? Any questions or curious about what this stuff means? Does anybody feel like they understand what a virtual machine is a little bit better?
Yeah.
Okay, good. Yeah. And yeah, hopefully this kind of project, it's like you maybe don't really know a lot of this stuff, and I'm sure if you like really start to go deeper and break into things, you're going to be like, what is all this stuff? But hopefully people, like these kind of projects can help people be less scared of like just the general concept and what it is. So that was kind of the goal for me, is just make something kind of fun and approachable, because if you look at even the thing where we get into making syscalls and stuff, this file doesn't really look any different than the thing that we wrote. I mean, it's the same thing. It's just a simple, small JavaScript file with normal JavaScript code. So if you know JavaScript, you should be able to follow this one step at a time. But yeah, the goal is to keep this really small and easy to understand, and just take it in kind of bite-size snacks here. Cool. All right. Well, if there's no questions on Slack, then I guess we'll close it up and go to Hack Night now. Let me go ahead and shut off the stream. All right. Thanks everyone who's online.